MDPs are, MDP is nothing but a decision process superimposed on a Markov chain. That's all it is. Okay, MDP is nothing but taking a decision process and throwing it on top of a Markov chain. So instead of simply classifying the system into states and finding the long-run probabilities, you want to make decisions. Let's say your car is failed in the morning, or let's say that a car is in 4 or 5 states, the best working state under the worst possible working state. Every day when you start your car and when you place your car in one of these states, you want to make a decision. Maybe when, let's say your car can be in 4 of these states, 0, 1, 2, 3. These are the 4 states. This is the best working state of your car. This is the worst working state of your car, which means it's junk. Okay, my car is here. Okay, but anyway. So what you want to do is, when you have these states in Markov chains, all you did was, okay, I start my car, I find the limiting probabilities, I find pi 0, I find pi 1, pi 2, and pi 3, right? And then you can find some expected measures of, how many times, this maybe state 2 is visited from state 0 in, let's say, 6 or 7 days, right? These are the kind of measures you computed. But you did not really make any decisions, right? You did not really make any decisions in Markov chains. So what MDPs are saying is, let's say you find your system in these states, and you have 2 decisions to make in every state. Either do nothing or repair. Even when you find your car in state 1, you either do nothing or repair. Same thing in state 2. You either do nothing or repair. Here you obviously have to repair. There's no choice. But you can decide to just not repair and junk the car, right? So these decisions are what make Markov decision process very, very powerful. Okay? So using MDPs, what you can find is an optimal policy depending on the state of your system. Okay? So MDPs, the idea of MDPs is really straightforward. What you want to find, the goal of MDPs when you're casting a problem of MDPs, is to find the optimal policy. Just like how when you're solving a linear programming problem, you want to either maximize costs, or no, you don't want to maximize costs. You want to maximize revenues or minimize costs, right? So there's an objective, and you have to make certain decisions within, how your decision variables behave. Right? So MDPs, the idea is just the same. The idea is very similar in MDPs. Let's say your car, let's stick to the same example throughout the class today. Okay, take the car, the best possible working state to the worst possible working state, 0, 1, 2, and 3, the increasing states of deterioration of your car. Okay, so what could be potential states of your car? What could you possibly do? You have 4 states, 0, 1, 2, and 3. Right? I could do nothing, repair, do nothing, repair, do nothing, repair, do nothing, repair. How many possible policy combinations do I have? It's not an MDP question, it's just an intuitive question. How many possible policies do I need to evaluate? 16 possible policies? 2 times 2 times 2 times 2? Different policy combinations, right? So when you're evaluating Markov decision process, what you're really trying to do is evaluate these policies in a very smart fashion. Okay? We want to develop some procedures to be able to assess all these policies, because that is all there is. In each state, you decided that you're going to make 2 decisions. Either you do nothing or you repair the system. So there's totally 16 policies that you can use for the system. But you want to find the optimal policy that either maximizes your revenue or minimizes your cost. In this case, since we're talking about a car, we'll talk about minimizing your costs. Okay, so you want to find that optimal policy. So is it always possible? What I'm saying here is really called the brute force approach or exhaustive enumeration. Okay, which means I take each and every policy, I find the cost. Find each and every policy, I find the cost. Okay, you think that's a smart approach? What if I have 25,000 policies to evaluate? You'll be here all year, right? So what MDPs say is they have given us, researchers have given us some nice, very compact algorithms to be able to, just like how your simplex algorithm is, just like how your simplex method helps you to move from one feasible point to another and evaluate those points. That's what you did in linear programming, right? When you're doing simplex method, what are you guys doing? You're really moving from, when you have the simplex method, all you're really trying to do, you have those constraints, you're trying to move from this point to this point to this point to this point to identify the best point, right? You guys agree with me? That's what you did in deterministic OR. The same idea, a similar idea has been proposed, but for MDPs. Not simplex method, we'll develop an algorithm. Simplex is also an algorithm. The simplex method is also an algorithm. It's a step-by-step procedure that terminates in an optimal solution. Similarly, MDPs, there's a professor called Richard Bellman who proposed a procedure that can be used to find the optimal policies. So that's what we're going to study today. Do you guys get a broad picture of what I'm trying to say? In Markov chains, you do not make any decisions. In MDPs, you make decisions at every stage. So it's a lot more powerful when you're studying real-life problems. Okay? What I'll do is I should have printed that handout. I have two handouts that I want to post. I'll scan them and put them online. Please take a look at those. Those are actually MDPs applied to real-life problems. Just like how Markov chains, I gave you a handout. I want you guys to see where MDPs are really used. Okay, so take a look at that. I'm going to post online today. So with all this in mind, let's go back a little bit to Markov chains. A little bit to Markov chains, sort of jog your memory a little. What was the fundamental principle of Markov chains? We said probability that xn plus 1 equals j given xn equals I, xn minus 1, xn minus 2, all the way up to x0 is the same as the probability that xn plus 1 equals j given that xn equals I. Right? That was the definition of a Markov chain, which means that the history of the states does not matter. Where you were before does not matter. So these guys here, you don't care about these states. Right? That was Markov chains. Now what I want to do is I want to throw a decision process on top of this. And what is a decision process? It sounds like a fancy word. All it is this. This is a decision process. Right? Each state, you have two choices. You don't know with what, you only know probabilistically how you're going to take those actions. You don't know with certainty that this action will be taken in this state. That's what you're trying to find. That's the idea of MDPs. But it's called a decision process because it's really a stochastic process. You really don't know beforehand what decision you're going to take. Okay? Just like how you don't know what state a system is in every day, you don't know what decision you're going to take in every state. So that's what you're trying to do. So what MDPs, the difference in MDP, now I'm trying to superimpose a decision process on top of this now. So I say xn equals I, comma, dn, semicolon, xn minus 1, dn minus 1, xn minus 2, dn minus 2, all the way up to x0 and d0 is the same as probability that xn plus 1 equals j given xn equals I, and you know the decision that you took when you're in state n. Write this down, please. If I'm going too fast, please stop me. Okay, I want you guys to write this down. This is very important. All I'm trying to do, if you observe the equation clearly, I just threw in a D, a decision process in between. That's all I did. Remember the fundamental assumption of Markov chains. Future is independent of the past given the present. Sounds philosophical, but it's very useful. It doesn't work that well in real life though. Right? If you go looking for a job, you wish the future was independent of the past, but what you do really matters. You wish your grades didn't matter, but they do, right? Okay. So what you did, observe the difference between this and this. This is the only guy that I added, the dn minus 1 are the only folks that I threw in here. That's the decision process that you threw in. So you superimpose a decision process on top of a Markov chain. That's an MDP. Okay, so this is called a Markov decision process. Okay? All right, what we want to do now is try to analyze a particular policy. Okay, let's take a policy for that system that we are studying. Okay, I want to analyze this policy and find the long run average cost of the policy. Keyword long run, right? That's what I want to find in the long run. If I follow this policy, what will be my cost? Do nothing, repair, do nothing, repair. So if my car is in the best condition, I won't repair, I won't do anything. When it goes to state 1, I'll repair it, get it maintained. If it's here, I'm not going to repair it like I do with my car, okay, and wait for it to fail. So you take a little bit of risk on your car, right? The check engine light shows up, and you just let it go, and it disappears, self-healing. Yes?
I was thinking, dumb. I was going to say if you repair it at state 1, won't it go back to state 0?
If you repair it here, it goes back to state 0, right?
Then how will it get to state 0?
You're absolutely right. I'm going to go there in just a second. So what we have, that's a very good question that Matt asked. The thing with Markov decision process is, with every action that you take, you have a separate transition probability matrix. Okay? So if you do not do anything, there is a transition probabilities of how the system behaves. And like you said, when you're in state 1, if you repair the car, if you choose to repair the car, it obviously has to go back unless the mechanic screwed up, right? So with each action, you have a specific transition probability matrices. So in this case, how many actions do we have? 2 actions, right? So we have 2 separate transition probability matrices. If there are 5 actions, you'll have 5 TPMs. If you have 500 actions, you have 500 transition probability matrices. Okay? This stuff is really advanced. What you guys are learning, many programs in the country don't learn MDPs at undergraduate level. Okay? This is really good stuff, very useful stuff. Okay? So let's take policy. I'm going to write the transition probability matrix for do nothing. Okay? Transition probability matrix for do nothing. And this is nothing fancy. It's got all the properties of a TPM. The rows have to add to 1, and the properties hold. It's just that for every action you take, you have a different transition. The way the system transitions to different states is different. So you have 0, 1, 2, 3, 0, 1, 2, 3. Let's throw in some arbitrary numbers, okay? These are really arbitrary numbers, and the reason I'm throwing in some arbitrary numbers is to show you some mechanics of how these things work. So let's say you don't do anything here. Let's say 0.1, 0.2, 0.3, that's 6, so there's 0.4. So what is this telling you? When you're in state 0, if you don't do anything, this is how it transitions. Are you guys with me? When you're in state 1, you don't do anything, how does the system transition? Let's say there's 0, 0.7, 0.2, 0.1. When you're in state 2, let's say you don't do anything, 0, 0, let's say 0.2 here, 0.4, and 0.4. Let's say this guy is 0.1, 0.2. I'm saying it's going to self-heal. There is a possibility that from the junkyard it goes back to your house, okay? 0.3, 0.3, and 0.4. Okay, so this is sort of just a made-up transition probability matrix. But I want you guys to understand this very carefully. Guys, write a little bit later. I want you guys to focus here. When you're in state 2, you do nothing. These are your possible transitions. Next day when you wake up, 0 probability that your car is going to be in state 0. 0.2 probability that it will go to state 1. 0.4 probability, it will stay in the same state. 0.4 probability, it will go to the worst case scenario. Do you guys see that very clearly? Everybody? Okay, wonderful. So that is P of do nothing. Let's write a matrix for, I'm going to erase this guy here. Let's write P of repair. What happens when you repair? I want to write the transition probability matrix for repair. Again, that will have all the properties of a TPM, 0, 1, 2, 3, 0, 1, 2, 3. If you repair it here, it goes back with 1 probability. Let's say maybe it doesn't get repaired. There's 0.5, 0.5, 0, 0, 0.2, 0.3, 0.5, 0, 0.1, 0.2, 0.3, 0.4. Okay? Just another transition probability matrix. Guys, write this stuff down. This is not there in your textbook. Write all this down, please. You're studying for your textbook has all kinds of fancy stuff. I want to explain as well. It's a nice bedtime reading. Okay. All right. So what am I trying to say here? I'm saying that if my system is in state 2 and I repair, these are the transitions. Right? That's what I'm trying to say. Now, I want us to go back to this problem here. I want to analyze this policy. I want to find out how this policy behaves. But when you want to analyze this policy, I said find the long-run average cost of the system. How do you find long-run probabilities? Pi's, right? You want to compute the pi's. What do you need to compute the pi's? The transition probability matrix? But I have 2, so which one do I use? Sort of extract from both the transition probability matrices, right? Do you guys see what I'm trying to say? You have 2 matrices, and this is a policy that you want to analyze. So you want to extract a single matrix from these 2 guys, okay, for analyzing this policy. and see if you follow me here. I want to call that P new. Okay, this is my new transition probability matrix for analyzing that policy. When you're in state 0, I don't want to do anything. So where do I grab the row from? When I'm in state 0, I don't do anything. So I go here and grab this guy. Is that correct? That will be 0.1, 0.2, 0.3, 0.4. When I'm in state 1, I choose to repair. Where do I get that stuff from? Go. When I'm in state 2, sorry, when I'm in state 1, I choose to repair. When I'm in state 1, if I repair, these are the possibilities of transition. Everybody with me so far? That'll be 0.5, 0.5, 0, 0. How about for the next one? What do I do for that guy? Go back here, right? When I'm in state 2, do nothing, pick this guy, and throw him here. It'll be 0, 0.2, 0.4, 0.4. Finally here, I decide to repair, so I go here and pick this out. Okay? Makes sense? Straightforward, right? So if I want to analyze a particular policy, this is how I do it. Once you have the P new, all you want to find is you want to find the pi's, right? Use a 5-step procedure, throw it in MATLAB, and get the pi's. But if you want to find the long-run average cost of the policy, you need an F vector, right? You need a cost vector that needs to go with it. But now, since we have 2 actions that you can take in every state, there will be 2 cost vectors. Is that right? There's going to be 2 cost vectors. If you do nothing, there'll be a F of doing nothing, which will be 0, 1, 2, 3 states. This will be $0, $0, $0, $0. You're not doing anything. Right? Same thing with F of repair. What would that be? If you repair, let's say, in the best possible state, which is 0, 1, 2, and 3. If you want to repair here, it probably will cost you, let's say, $5 or something. Okay? Really cheap mechanic. Nice guy. If you go here, maybe 100, 300, and let's say it's $1,000. Okay? So this is your F do nothing, so F repair. So remember, every action will have a transition probability matrix. Okay, don't forget that if there's 5 actions in a state, you have 5 transition probability matrices. Okay? Now, I want you guys to, so we found the P new, and now we want to compute. But based on our policy, what was our policy? The policy that we chose was, we said do nothing, repair, do nothing, and repair. So what's your F new based on this policy? Absolutely. 0, 100, 0, 1,000. Right? And all you need to do next is do pi times F new to assess that policy. In the long run, if you adopt that policy, what's it going to cost you? Okay, so on the test, if I ask you to give you a policy and ask you to analyze it, this is what I expect you guys to do. But is this a good way to solve a large-scale problem? This is not a smart way to solve a large-scale problem, right? We just picked, imagine all this work that we did is for analyzing one policy. All these steps that we did is for analyzing one policy. Would you do this 16 times? You would not, right? Then we wouldn't be called industrial engineers, right? We got to find efficient ways of doing things. So what Richard Bellman, professor from I think Stanford or Berkeley, I don't remember which one of those places, gave an algorithm or an equation. So Richard Bellman, okay, showed that optimal policies can be obtained by the following equation. Okay, he derived an equation. Okay, so he said value of state I is nothing but the reward Ri. Just write this down and we'll well, let's write from the beginning. Min slash max A in AI R of IA plus beta summation J in E PIAJ times Vj. Okay? Let me write this a little clearly. PIAJ times. Okay? So this is called the Bellman optimality equation. Yeah, that's called the Bellman optimality equation, and we'll talk about it in just a second. Just add in the end for all I. Okay, add for all I in the end of that equation. Okay. Right. So what I want to do, I want to write this a little clearly here and explain each and every term in that equation. I'm just going to rewrite it here. V of I is minimum or maximum of A in AI R of IA plus beta times summation J in E probability I A J times Vj. Okay, so write all these definitions down now. Vi is really the value function in state I. All this equation boils down to, just hold on from writing just a second. All this equation boils down to is a set of linear equations. Okay, you solve these linear equations in iterative fashion, you find what are called optimal values. And these values will tell us what the best policy is in every state. So instead of doing this brute force or exhaustive enumeration approach, we'll use a smarter approach. Just like the simplex algorithm, where you develop those tables, all you're trying to do in simplex is go from one point to another, right? You're going from one corner point to another. That's all you're trying to do. This is very similar. You're trying to move from one value to another until you reach the optimal value, and that optimal value will give you the optimal policy. Okay? All right. So this is a value function in state I. A is the action that is taken. AI is the action space. R of IA is what is called the immediate reward or immediate cost. Beta is what is called the discounting factor. J is again a state of the system. E, as we always say, is a state space. P of IAJ is the probability of taking action A and going from state I to J. You take action A, you go from state I to J. That is PIAJ, because now you have action-dependent transition probabilities. You simply included the A in between. It refers to a transition probability matrix. That's all it is. But now it's action-dependent. Depending on the action you choose, your system transitions in a different way. And this Vj is nothing but the value function in state J. Okay? It's a value function in state J. It's very important to understand every term of this equation and write it in English. It's always very helpful when you go back home to look at your notes. You need to learn how to read that equation in English. Okay. So once you have that, a few more minutes. Let's discuss something really quick. So this is the Bellman's optimality equation. So what Professor Bellman did was Bellman proved that the optimality equation he proved, okay, can be used to derive the optimal values and those values can be used to obtain optimal policies. Okay, so he really proved mathematically that this thing can be done. Okay, that there exist. He wrote, I think, a seminal paper in I think 60s or early 50s, showing that that equation, this guy right here, can be used to obtain optimal values, and once you have optimal values, you can get the optimal policy. But he did not tell us how to solve that equation. He proved mathematically, which is fun, but how do you use it? There's another professor called Ron Howard, not the movie director, okay? Ron Howard is a professor, I think, in Stanford, who gave an iterative algorithm that can be used to find optimal policies. and we'll look at it on Tuesday. Okay. So we'll talk about what is called the value iteration algorithm and what is called the policy iteration algorithm.